Hi IB, we're going to go ahead into 3F, which is our last topic for this chapter, and that is our natural exponential. We have been looking over the last couple days on what exponential growth and decay look like and how to graph them. So we've started to notice that you have a basic form of an exponential equation. You have a coefficient that affects the stretch. You have a base that also affects your, whether it's increasing, growing, or decreasing. And then you have an exponent with a possible horizontal shift. So that will shift your graph left and right. And then we've also been talking about this additional value that now shifts your graph up and down. So similar to the different parameters in your previous functions, quadratics and lines that you guys have been studying. However, there are a couple numbers that come up a lot in mathematics, and one of them is pi that you guys are pretty familiar with. So pi is used as a ratio for circumference and diameter of a circle. However, you now have a new number that we're going to be looking at, and we'll explain a little bit more about what this number e actually represents. But it comes up a lot in exponential data, and it winds up being approximately 2.718281, and then it continues. So similar to pi, where we estimate it as 3.14, however, it's an irrational number, so it will go on forever. And it was found, right, when we start to work with these various ideas a lot, one number continues to come up. And pi was for circles, and e comes up a lot with exponential data, really. So we'll take a look at that a little bit more in class. But right now, just think about e as a new base. So our new base is 2.7 approximately that we're going to use for looking at some of our data today. So looking back at the investigation, you guys graphed a lot of graphs that looks like a base of 2 raised to the x power, so it was an exponential growth. So now if we had e to the x power, you're really just thinking of that as 2.7 approximately to the x power. So it should be just slightly steeper than that 2 raised to the x power. So my base is getting really close to what a base 3 graph would look like. So before we move on into talking more about e, we're going to take a moment just to revise what you guys should have gotten from last class when we were graphing exponential functions for the first time, right? So I'm going to take a blue color to draw 2 to the x plus 1. And notice that my base is 2, and I'm adding 1, so that is my d, my vertical shift. Then I have 2 minus 2x. I'll use green for this one. And notice this one I could rewrite, just to make sure I'm noticing that the negative is your coefficient, your 2 is your base, and then you have this additional 2 that's added on to the end. So don't hesitate to rewrite your function if you can write it in a way that's a little bit clearer for you. I'll use red for the C graph. That one's actually in a nice form. However, if it helps, think of this 2 to the negative x is really going to be 2 raised to the negative 1x. So I could rewrite 2 to the negative 1 as you guys know, 1/2. So we should see a decay for this one. Because that exponent is negative, that means I actually have a fraction as a base that's between 0 and 1. And then for the last one, I'll actually use black. And again, I would look at this again slightly differently. So I would start with the negative as my coefficient. 2 is my base, but since it's raised to the negative x, let's write that as negative 1/2 to the x power. And then I have this additional 3 added on the end. So I've just changed the original form of the equation so that they look a little bit more standard, so I can compare them to my standard form of the exponentials, which is my a times b raised to the x, possibly with a horizontal shift, and possibly with a vertical shift. All right? So at this moment, I would go ahead and pause the video, try to graph these 4 by hand, check them with your calculator as well, and then in a moment, go ahead and push play and see if you agree with what I've got. My blue graph, I have a horizontal asymptote at 1 because I was shifted up 1. And now I have a couple more points. I just substituted in 0, I substituted in 1, 2, and 3, because that's what I could fit on my graph. And then you know that to the left, you're just going to get smaller and smaller and smaller as you head toward that asymptote. Let's look at the green function now. So my green graph, I have a horizontal asymptote at +2 because I had that vertical shift up 2, and it's reflected because of the negative a coefficient. Let's go ahead and look at our red graph. For our red graph, we had a vertical shift up 3, so now my horizontal asymptote is up at 3. And again, we knew it was going to be a decay because I had a negative exponent, which makes my base a 1/2, a fraction between 0 and 1. So I substituted in a few points in order to get an accurate graph. And then let's look at our last one. And last but not least is the black graph, which has the same horizontal asymptote as the red. So they're right on top of each other. However, I do have a decay, but because of the negative a value, my decay has been reflected over that asymptote, really. So now that I've been reflected, it looks like it's actually increasing from left to right, even though it's a decay. But because it's been reflected, after we drew the decay, it's been reflected because that's outside of the brackets, so it does take the whole graph and reflect it downwards. All right? So my second challenge to you is push pause and see if you can actually figure out what the domain and the range would be. So first, just start with domain and range. And then go ahead and push play and see if you agree with me. So looking at all 4 of these graphs, if you follow any of these graphs from all the way as far left as they'll go, so if we just look at this blue one for a moment, if I start all the way from the left, it's coming from -infinity, and if I follow it to the right, it's going to keep getting wider and wider and wider as it goes upwards. So if it continues to go wider, that means that I could continue tracing x values all the way to +infinity, and they'll match up with y values that are way up in the sky, right? Way up high, all the way to infinity and beyond. So for all of these, if you choose the leftmost point and you just follow the graph toward the right, you're going to be able to go on forever. So all x values will eventually match up with corresponding y values. So any x value we can choose for our domain. So all of them are all real numbers. Let's see if our range is limited at all. Go ahead and push pause and see if you guys agree with these. So after our discussion in class, we realized that the range would be affected by your horizontal asymptotes. So if you guys notice, for the blue, your graph can have any y value that's above the horizontal asymptote at 1. So I can take any y value greater than 1, but it will never actually touch the horizontal asymptote at 1. So not equal to, just strictly greater than. And then that goes the same for the other asymptotes in the other colors, okay? So I can actually, at this point, go ahead and write down my asymptotes. So if you guys come down to the very, very last line where it says asymptotes, I only have horizontal asymptotes that we collected from class the other day as well. So I can go ahead and write down my horizontal asymptotes for all 4 functions. Go ahead and try that and see if you guys agree. All right, guys, so go ahead and note to the different asymptotes. And since they're horizontal, they'll be in the form y equals. The last part that we haven't talked about, but we've talked about a little bit in class, is looking at the end behavior of the graphs. So if you put your finger on each of these graphs, I put my finger right here on the blue graph, and if I follow the graph to the right, so as x gets bigger, I would be going toward the right, what's happening to your y value? So that's the question then we talk about following x as it goes to positive or negative infinity. Your answer is going to be, what is happening to f of x? As it approaches, using that arrow to say approaches, either does it go to a positive infinity or does it go down towards negative infinity? So just looking at the blue graph, if I follow my graph from the left to the right, going toward positive infinity along the x-axis, you'll notice that my graph is going upwards also toward positive infinity. So I could say my y value is also going up. Whereas if I followed my graph to the left, to negative infinity, so if I came down from the top here, and I went down in this direction to the left, I'm noticing that I'm getting lower, and I'm actually starting to approach the asymptote. I'm not actually going all the way down to negative infinity, but I'm getting lower, and my f of x is starting to approach the asymptote at 1. Okay, so let's take a look at the green one. I'll walk you guys through one more, and then I'll let you guys try the last two. For the green graph, as x goes toward positive infinity, my f of x is going down toward negative infinity. But now if I follow my graph from the right side to the left, so coming up this direction, I'm actually getting closer to my asymptote again. I'm not actually going to go all the way up to infinity, but I am going to get closer and closer and closer to 2. All right, and we'll talk about this idea a little bit more in class as well, but go ahead and give a shot for the last two, the red and the black graphs. All right, so thinking about this idea with the red and the black, they both go toward the asymptote as you are looking to the right side of the graph. So when you come from the left and go to the right, but if you start on the right and go left, they go toward positive and negative infinity. All right, guys, so that was a little sum up, a little summary of what we've been doing over the last couple days. So now if we introduce a new base, we should be pretty confident that we can make an x and a y table, and we can substitute in some values, and we can now go ahead and try to figure out, well, if I know that e is representing a number that's really close to 2.7, okay, what can I actually get out as my values? And I should sort of know already that I don't see a plus d value, so I should know where my horizontal asymptote is. I don't see a minus c value, so I shouldn't really have a horizontal shift. So it should be centered right around that x-axis and y-axis, right in the center. So go ahead and try to substitute in a few values, and let's see what we get. So at this point, not even knowing a whole lot about e as a natural exponential, I can go ahead and graph it, and I already know that I have a horizontal asymptote at y equals 0. I know that I'm hitting the y-axis at 0, 1. I know that at 1, I'm about at 2.7, which is that e value that we're just introducing. And I know that it will increase by that same amount. All right. So we already know a lot about this graph, even without knowing a lot about what this natural e actually is. So guys, working with e is going to be very similar as working with pi. On your TI Inspire, you have e on the button on the left. You guys will notice that as soon as you push that e and push enter, it'll give you the exact value of e, which is the original value I gave you guys. So let's go ahead and find out. If I take e squared, just practicing putting that in our calculator, and it says to round it to 3 significant figures. So this one's going to wind up being about 3 points. And then it's 389. So for 3 significant figures, I'm going to have to use 7 points and then 39. Okay? If I look at d here, just as an example for how we work with e, I would rewrite this as square root of e, or e to the 1/2. Same thing with part e. Just remember that's 1 over e is the same thing. So starting to bring back some of your rules of indices, and then we can just use the e value, the exact e value. So you actually want to use the e button on your calculator, and then raise it to the 1/2 power, or take the square root of it, however you're going to enter it into your calculator. And then we want to write down as close as possible what our approximation would be. So square root of e is going to wind up being about 1.6, and then we'll round that off to 5 for 3 significant figures. And then bringing back our rules again, rewriting with powers of e. So let's take a look, for example, at c. If I want to rewrite it as a power of e, I'm going to remember that e is now raised to the -2 if I bring it up to the numerator. Or, for example, with d, I have e to the 1st power, and then e, square root of e is e to the 1/2 power. So I have the same base. Now my bases match as e, and I add my indices. So I have e to the 3/2 if I write it with my index laws. All right? So just a little bit of an introduction to the letter e, the natural exponential, and we'll work with it more tomorrow in class, guys. Have a great night.